Alors, bonjour tout le monde et bienvenue à ce colloque des sciences mathématiques du Québec. Welcome everyone to this mathematical science colloquium organized jointly by CRM and ESM. It is our pleasure today to welcome Maria Ntekoume from University of Concordia. Maria is an assistant professor there. She just started after being a GC Evans instructor at Rice. She holds a PhD from UCLA, which she obtained in 2020, so she's still young and eager and full of energy. Her research area is nonlinear dispersive PDEs and integrable system, and today she's going to talk to us about critical well-posedness for the derivative nonlinear Schrodinger equation, dispersion, and integrability. Merci de votre présence. Maria?
First, I want to reassure the non-analysts in the audience that hopefully this will not be too bad for you. And by the end of this talk, you will have at least gotten some perspective on how we treat these dispersive and integrable problems. So we'll try to start very slow. Okay, so the main object of this talk is this PD right here. So this describes the evolution of Q, which is complex valued. And let me see now if I can point. So can people, no, I don't think I can point. Okay, I can point like this. That won't help too much. Okay, so Q is complex valued, and it depends on two independent variables. It depends on time, t, which takes values on r, and it depends on a spatial variable, x, which in this talk we were going to assume that it is one-dimensional. It takes values on the entire real line. So let's read together this equation. So we have I times the time derivative of q plus two derivatives in space of q. So whenever I write prime, I mean derivative in space. And that is equal to negative I times the derivative of q squared q. That's our equation. So this equation has two parts. It has a linear part, which is the linear Schrodinger equation, the green one right there, and it has a nonlinear part in which we see that we have a cubic nonlinearity with a derivative. So that's how the equation gets its name. It's a nonlinear Schrodinger equation with a derivative, so we call it the derivative nonlinear Schrodinger equation. And in this talk, we are going to be interested in the Cauchy problem when I put some initial data at time 0, Q naught, and Q naught is going to be in some space. I'm not going to tell you yet what kind of space. And the question that we are interested in is that of well-posedness, meaning, do I have a solution? Is my solution unique? And does it depend continuously on the initial data? This is perhaps the most fundamental question that one can ask about a PDE, and that is the focus of this talk. So what we're going to try to answer is what is the optimal space X, on which we can consider the question of well-posedness and hope to get global well-posedness. Can we get our hopes, right? Will our conjecture be true, and how? So that's the main question. And our two allies in this exploration are going to be the two main features of the derivative nonlinear Schrodinger equation, which are that it is this, yes. That will also be part of the question, okay? Because yes, of course, first I need to know local, right? Yes, that was, yes, I am interested in both, okay? But my goal is to also get global at the end, okay? Okay, so our two allies are the fact that this equation is dispersive and completely integrable. And if these words mean nothing to you right now, that's completely okay, because I will spend the first part of my talk explaining what these words mean. So first of all, dispersion. What is dispersion? So to say that my equation is dispersive, I have to look at the linear part. That's where the characterization takes place. So very informally, a linear evolution PD is called dispersive if, assuming that I'm posing this equation in the domain without boundary, its solutions are going to spread out in space as they evolve in time without dissipation. So the example to keep in mind is what happens if I am in a lake, a very, very large lake. Let's imagine I'm in the middle of the lake, so I cannot see the boundary, I cannot see the shore, it's too far away from me, and I drop a stone in the lake. I'm going to have some perturbations of the surface of the lake, right? Some little waves. And even if I start with perturbations that are very localized and, let's say, tall, close to where I dropped the stone, as it evolves in time, I expect these little waves to spread out, right? To their amplitude to diminish and spread out. So that's the picture to have in mind. But of course, this is very informal, and this is a mathematical talk, so I should make that a little bit more rigorous. Okay, so let's look at the most famous example of a linear dispersive equation, the linear Schrodinger equation, which is of course very relevant to what I'm going to say later, right? Okay, so this is what the equation looks like. We already saw it, and it's a linear equation, so I can solve it. How do I solve it? If I take the Fourier transform in the space variable, and then what is going to happen? Okay, yeah, I cannot point. Well, the Fourier transform in the space variable is going to commute with the time derivative. So here I'm going to get from the first part the time derivative of the Fourier transform at frequency xc. Now for q double prime, what happens when I take the Fourier transform of a derivative is I get a factor of I times xc in front, and I have two derivatives, so I will get two factors like that. So I get negative xc squared times q hat of xc, and that will be equal to 0. But now if you look at that for any fixed xc, this is a linear ODE, so I can solve it, which I do, and I get something like that. So I get that the Fourier transform of my solution at time t, frequency xc, is going to be the Fourier transform of the initial data at frequency xc times e to the negative I xc squared t. And there are a lot of things that I can read from this formula right here. First of all, you see that what does evolution under the linear Schrodinger equation do to my solution? It takes the part of the solution that lived in frequency xc, and it just sends it traveling with speed xc, right? So in particular, we see that different frequencies are going to travel at different speeds. Frequency xc travels with speed xc, and large frequencies travel faster. You can see that this is you can compare it to the wave equation, right? Where frequencies, different frequency parts travel with exactly the same speed. So you get the profile of your solution maintained, just traveling in space. This is not what happens here. Different parts travel with different frequencies, travel with different velocities. And this is the formal actual definition of dispersion. Large frequencies travel faster, okay? Moreover, from this, the formula that I wrote here for the Fourier transform of my solution at time t, we see that the Fourier transform at time t has exactly the same absolute value as the Fourier transform at time 0. So then, okay, I can integrate, right? I can square that and integrate that, and then I get that the L2 norm of the Fourier transform at time t will be equal to the L2 norm of the Fourier transform at time 0. And then by Plancherel, I have that the L2 norm of my solution at time t will be exactly the same as the L2 norm of my solution at time 0 of my initial data. And that is going to happen for all t. So I have conservation of the L2 norm, conservation of mass. And now you can compare that perhaps with something like the heat equation, where we have if you compare what happens to the Fourier transform of your solution in the heat equation, what happens? You don't have this I here, right? So you have actual decay of the Fourier transform, right? And that gives you actual decay of the L2 norm. You lose mass. That is not what happens here. The mass stays the same, right? Okay, so we have conservation of mass. And I can actually iterate this argument and show that the L2 norm of not just the solution itself, but any derivative of the solution will be preserved. Now, I wrote down again the formula that I showed you at the beginning. And okay, so what does that show? It shows that I can write my solution, I can express my solution at time t, in a way using just the Fourier transform of the initial data. Well, okay, I could write down what the formula for the Fourier transform is, and I would get a formula where I don't have the Fourier transform, but the initial data itself, right? And if I work that a little bit more, I could get a very, very nice, in my head, formula. Maybe it would not be that nice for you, so I will refrain from showing you what it is. And instead, I will show you an estimate that I can get using that formula that I'm hiding from you, which is what we call the dispersive estimate. And it shows that I can bound the L infinity norm in space of my solution in terms of the t to the negative 1/2, the time that I'm looking at, to the power negative 1/2 times the L1 norm of my solution. And that really captures the dispersive effects of the linear Schrodinger equation. Why? It tells me, first of all, that the solution has a decay time, right? I have t to a negative power. I need to have decay. Also, it shows me that even initially localized wave packets will have to spread out, because since I'm pushing my L infinity norm to go down, if my amplitude has to go down, but I have to maintain the same L2 norm, I am forced to spread out in space. These can also be seen to have some kind of smoothing effect. I'm telling you, I'm starting with initial data in L1, my solution is going to be in L infinity. But that is not the smoothing effect that you usually have in mind, where you gain some derivatives, right? We don't have that for the linear Schrodinger equation. We don't expect to gain derivatives. But instead, we can gain derivatives in a more complicated, in a more subtle way. We have a local smoothing result. So locally in space and on average in time, I'm going to gain half a derivative. What do I mean by that? If I start with initial data in L2, then I will be able to bound the L2 norm, not of Q, but of the derivative of half a derivative of Q, but only if I integrate, let's say, on the ball of radius 1, and I average in time. Okay, and this truly is a dispersive effect. Why? What did we say that dispersion means? Dispersion means that high frequencies travel fast, right? So if I only look at the ball of radius 1, then very quickly the high frequencies are going to evacuate that compact interval, right? And then, well, what is left behind? Only the lower frequencies, and lower frequencies are smoother. So I have gained some regularity, but only locally and only in average in time. Okay. So now that we understand a little bit better what the linear Schrodinger equation is, let's look at nonlinear dispersive PDEs. And the two examples that I have written down here are perhaps the most famous nonlinear Schrodinger type equations. It's when I have, okay, I keep trying to point, when I have a nonlinear Schrodinger equation with a power type nonlinearity, where here you can look at the nonlinearity here. I have a plus or a minus sign, and then q to the p minus 1 times q for p greater than 1. Or I can have something like the derivative nonlinear Schrodinger equation that I'm interested in. And as we said, we're going to explore these kinds of equations under the lens of well-posedness. And okay, so I asked for the derivative nonlinear Schrodinger equation, and now I can ask it more generally. What is the optimal space, right, in which I hope to have well-posedness? Well, perhaps before that, what kinds of spaces are natural to explore, right? And for these kinds of equations, the natural spaces to investigate well-posedness are Sobolev spaces. So if you let me refresh your memory a little bit what Sobolev spaces are. So Sobolev space is HS coming two flavors, the homogeneous H dot S, where what I demand is that the S derivative of Q is in L2, and the non-homogeneous Sobolev spaces HS, where what I demand is that up to S derivatives of Q are in L2. Okay. And why are these natural spaces to investigate well-posedness for these equations? Well, for one, the linear problem is well-posed there. We saw that we have conservation of all of these norms, right? So now I want to show you some heuristics about how to start investigating well-posedness for such a problem, starting with the power type nonlinearity Schrodinger equations. So when you give me an equation like that, the first question I ask is, do I have any symmetries? And in particular, do I have a scaling symmetry? For equations like that, I do. So if I can take, if you give me some solution Q, I can rescale it in a way like that for any positive parameter lambda and get another solution to the same equation. And then I ask, for which homogeneous Sobolev space will the norm stay invariant under that scaling? Okay, so that's what I ask. And depending, in this case, depending on what p is, I will get a different answer. For example, for the cubic nonlinear Schrodinger equation, when p is equal to 3, the critical space is h dot negative 1/2. For the quintic NLS, when p is equal to 5, the critical space is L2. Well,
sorry, could I just ask a question quickly?
Yes.
I mean, p equals 3 is integrable and p equals 5 is not. So isn't there some big qualitative difference between the two cases?
Is there some, sorry, I didn't hear the question very clearly.
I'm saying that the p equals 3 case,
Yes.
that is integrable. There's
Yes.
a linear lax equation associated
Yes,
to it,
yes.
but not for p equals 5.
Yes.
So that must make a big difference in the qualitative behavior, doesn't it?
Yes, it will. So this is just, okay, so this is just a heuristic, okay? What the critical space will not change because okay, I defined what it means to be the critical space exactly by this, right? It has to preserve, it has to be the norm that is preserved under the scaling, okay? Now, whether that will coincide with the optimal well-posedness result that I will have or not, that's a different question, okay?
But I'm just asking, is there any feature that picks out the p equals 3 case, because that is integrable, so that has a huge number of, I mean, it's got an infinite number of conservation laws, and the
Yes.
others do not.
Yes, not at this level, okay? Not at this level. This is just, this is just a little calculation that is going to give us some conjecture, okay? This is just going to give us some heuristics, and this is something that works for all nonlinear Schrodinger equations, all dispersive equations in general, okay? This notion of
So at this
criticality,
stage,
but
integrability
yes.
doesn't play any role.
To determine what the critical space is, no.
Okay.
No. And once I know what the critical space is, I can form a conjecture, okay? So what I expect is that if I start with regularity more than the critical, with initial data more regular than the critical than in the critical space, I expect things to go well and I expect to have well-posedness. If I start with less regularity, I expect things to not go well and have ill-posedness. And exactly at the threshold, I expect things to be extremely tricky, okay? So overall, usually we expect that this critical space is exactly the best that we can hope for, but to get there, we know that we're going to have to work very hard, okay? Things are going to be extremely delicate. Okay, so that just gives us some conjecture. Whether it is always true or not, I'm not going to tell you, okay? Okay, so now what about the derivative nonlinear Schrodinger equation? Again, it has a scaling symmetry. If you give me some solution Q, and any lambda, I can rescale it like that, and this Q lambda is going to be a solution as well. And for this equation, it is the L2 norm that is left invariant under the scaling, so the problem is L2 critical. But L2 has another significance for this equation. The L2 norm is preserved under the flow, okay? And that makes it even more interesting for us when the critical norm coincides with the conservation law. So based on what I told you before, we can now form a conjecture that the best space, the optimal space that we could hope to get is L2, right? And since it is the critical space, we know that in order to get there, we would have to work very hard and would be difficult. Now, if I want to construct solutions, how am I going to do that? What I am going to write here is a general idea that works for any kind of nonlinear type Schrodinger equation, right? So I'm taking any kind of nonlinearity f, some initial data q naught, then I can write down Duhamel's formula, which is pretty much variation of parameters, right? So what does it tell you? It tells you that your solution at time t can be given by taking your initial data and evolving it under the linear evolution for time t, and then adding to that the combined effect of the nonlinearity for all times 0 between 0 and t, and then the nonlinearity, the part of the nonlinearity that kicks in at time s has time t minus s to be smoothed over by the linear flow. Okay? So that's Duhamel's formula. And the way that we usually approach at least the question of local well-posedness for a dispersive equation like that is using a contraction mapping argument. So if we consider the mapping phi that takes Q to the right-hand side of Duhamel's formula, we observe that in order for Q to solve the PDE, it will have to solve Duhamel's formula. So P of Q will have to be equal to Q. So finding solutions for my PDE equates to finding fixed points for phi. So the goal here is to find some suitable space S so that F is a contraction on that space. Now, that sounds deceivingly simple, right? You might think, take S to be your Sobolev space, right? Okay, usually you have to take some cleverly defined subset of that, but often even that doesn't quite work to show that it is a contraction, and you have to work much harder. And there have been lots of different, very complicated spaces that have been defined specifically to make an argument like that close, okay? But if you can find such a space as S so that phi is a contraction, then you will be able to construct, at least locally, a solution, and you know that this solution will not just depend continuously on the initial data, but uniformly continuously, right? Now, another little piece of heuristics for you, when I introduced these power type nonlinearity Schrodinger equations, I told you that they can come with a plus or a minus sign, and this sign actually makes a difference. Let me show you why. So when it's plus, we call the equation defocusing, and that represents repulsive self-interactions. When the sign is negative, we call it focusing, and it represents attractive self-interactions. And I can give you an example here to get some idea. So if I assume that I have some solution Q that is e to the, I can decompose it into a t-dependent part and an x-dependent part. The x-dependent part is e to the I cx, so a single frequency, right? Then I can actually solve that, get an explicit solution, and I see that my solution is a times e to the I cx minus c squared plus or minus a to the p minus 1 times t. So it is, if I remove that, it's exactly what I would have in the linear case, right? If I remove the a up there in the exponent. Okay, so what does it show me? In the defocusing case, remember that this c squared t, that was exactly the thing that was being added when I was solving under the linear Schrodinger equation, right? That's exactly the dispersive effect. So in the case when I have a plus sign, this extra nonlinearity can only enhance the dispersive effect in a sense. But in the case that I have a minus sign, it is actually working against it, right? They are in direct competition, c squared minus a to the p minus 1. So what I expect is that when I have small initial data, well, I expect the dispersive effects to dominate and to have well-posedness. But when I have large initial data, I am scared. I expect that it is possible to have focusing behavior. The nonlinearity will win. And I can have things such as finite time blow-up, things concentrating in space, or I can have solitons. Now, what are solitons? Solitons are really what I get when I have the dispersive effect and the nonlinear effects in some kind of a weak balance. So what do the dispersive effects tend to do? They want to spread my solution out, right? And the nonlinearity, the focusing nonlinearity, tries to concentrate my solution. What is the balance of that? Something that doesn't spread and doesn't concentrate maintains its profile. So that's exactly what solitons are. They are wave packet solutions that maintain its shape and just travel in space with constant velocity. Another interesting feature that solitons have is that they interact with each other in a very particular way. More specifically, if I have solitons that travel with different speeds, if they meet each other, they're going to collide. But once they continue moving, they will emerge with the same profile as nothing ever happened. So they interact elastically like particles, and that's what gave them their name. It's solitons like electrons or something like that. Okay. So the first description of solitons dates back to the observations of John Scott Russell from 1834. So this guy was on his horse along a canal in Scotland, and he was on this, he was walking, he was riding his horse along the canal. There was a boat in the canal, and suddenly the boat stopped. And there was a little mass of water in front of the boat, traveling at the same speed as the boat. Once the boat stopped, this mass continued traveling. And he noticed that this mass of water continued traveling without changing its shape, without changing its speed. So he kept following this mass of water for quite a long time, and then afterwards wrote his experience with it. He called it the great wave of translation. And okay, that sounds very interesting, but in fact, this observation gave rise to a lot of interesting mathematics. In particular, it led to the derivation of a very important PDE, the Korteweg-de Vries K-to-V equation, just to explain why solitons like that are consistent with what, the equation and what we see in nature is consistent. And this K-to-V equation afterwards has had a very long career. It's very famous. It is very well studied. It has been shown to be the first and perhaps the most famous completely integrable equation. Which now brings me to the fact that I owe you a definition of what complete integrability is. And perhaps I will disappoint you, but there will be no definition because there is no definition. So instead, what I can do for you is give you a list of symptoms that if you see them, you can say, yes, this is an integrable equation. So here's a few of them. First of all, it's the existence of infinitely many conservation laws that we just heard a few minutes ago about that. So indeed, the derivative nonlinear Schrodinger equation has infinitely many conserved quantities. The square of the L2 norm, the mass that I already told you about, it also has its Hamiltonian right there. It has another one that I wrote down for you. You see, they get more and more complicated. I will not write anymore because I don't think anyone would be able to pay any attention to it anyways, and of course, there are infinitely many. I'm not going to write down infinitely many of them. But there are infinitely many of them, and maybe you already notice a pattern. They all look like integrals of some polynomial of Q and its derivatives, and I have more and more derivatives the further down I go. So the first one is the L2 norm. The second one kind of looks like an H1 half norm. The third one kind of looks like an H1 norm, of course, plus other things, right? Okay. Another feature of completely integrable equations is the existence of a Lax pair. What is a Lax pair? It's a pair of operators, L and P, that depend on Q, okay? And when is it a Lax pair? It's a Lax pair when this thing right here holds. So when L and P satisfy this equation, the derivative of L is equal to the commutator in P and L, if and only if the Q that I plugged in there is a solution to DNLS, okay? And why is this interesting? It is interesting because this equation right here encodes a lot of hidden structure. In particular, because of this equation, we can tell that the spectral properties of the operator L are going to be preserved under the flow. And kind of hand in hand with that, another feature of completely integrable equations is that they admit an inverse scattering theorem. So what does that mean? I will very, very roughly sketch that. Oh, I'm not sure if okay, I do have a little bit of chalk. So what does this inverse scattering transform that I've told you about mean? So I have some initial data, right? Then if I'm lucky, perhaps from that, I can extract its scattering data. Of course, that is going to be at time 0, okay? The magical thing is that this scattering data now evolve in time in a very straightforward way, linearly, okay? So then once I know the scattering data times 0, I can find them at time t, okay? So that was the direct scattering. Now what I have to do to construct my solution is invert this process. So that is called the inverse scattering transform, constructing from the scattering data the solution itself. And if I can do that, of course, I have a solution and I have an exact formula for my solutions, okay? So it's kind of magic, yeah, being able to solve a nonlinear PD. The only downside for that, at least for what we're talking about today, is that in order to properly define the scattering data, so be able to talk about the direct scattering and the inverse scattering transform, I require some more niceness of my initial data. I require some decay in space, okay? Which in general, if you're just in a Sobolev space, you don't have. Okay. Give me 1 second. Oh, that's okay. For now, it's okay.
Sorry, would you be kind enough to actually write L and P down?
Right, what?
to give expressions what the lax operator and its pair are.
Later, yes. Yes, I will show you later, of course. Okay. Okay, so now it is time to go back to our main question, completing the well-posedness picture, okay? And in recent years, there has been a lot of advances in completing the well-posedness picture for several integrable dispersive equations. For example, the KdV equation that I mentioned earlier, and the cubic nonlinear Schrodinger equation, which is in fact completely integrable. It is the only one out of the power nonlinearity ones that I showed you that is completely integrable. And what has been noticed is that in all these cases, the picture looks very peculiar, and it looks very unique and unlike other non-integrable dispersive equations. So here, maybe I need to decode what these colors mean for you. So the blue color, the blue point, is the critical regularity. Okay, so I told you earlier, I give you the critical regularity, you can make your conjecture, right? Above everything is good, below everything is bad. Red means ill-posedness. So you see that both of the equations here, KdV and cubic nonlinear Schrodinger equation, are actually ill-posed at the critical space. Okay, and actually for KdV, we have quite a big gap where we would expect it to be well-posed, but it's not. The green region up there is where I have global well-posedness in a very nice way, when I have also uniformly continuous dependence on the initial data, which is exactly what I can get using contraction mapping arguments, okay? Which I told you, it's the main tool that we usually use, okay? Okay, so these things had been known. The red region and the green region had been known for quite some time. The new things that only emerged recently are these yellow regions. And these yellow regions are the regions where your equation can be well-posed, but only have continuous dependence on the initial data, not uniformly continuous dependence on the initial data. And for the non-integrable dispersive PDEs, this yellow region does not exist. You have the red and you have the green, and there's nothing else in between. Okay, you don't have this additional space. Okay, and another feature that I want to showcase here and compare these two is, as we said earlier, for KdV, we have that the optimal well-posedness result is quite far actually from the critical space. For the cubic NLS, it's not that far, but still it's not at the critical space, right? The critical regularity is just missed. What about the NLS? So let me recapitulate what we have already seen. We have seen that this equation is dispersive, it is completely integrable. We found the scaling symmetry, and we found that L2 is the critical space, and we formulated our conjecture, right? That I hope to have global well-posedness in L2. And this conjecture is exactly what I want to talk about for the remainder of the talk. And it's based on joint work with Ben Harrop-Griffiths, Rowan Killip, and Monica Visan. Before I tell you anything more about this conjecture, I have to go back to my heuristics. If you remember, okay, the first part of heuristics that I showed you were about the critical space, right? But then I showed you another one about the focusing versus defocusing behavior. I never told you if DNLS is focusing or defocusing. Unfortunately, maybe let me go back here. Unfortunately, you cannot just say if it is focusing or defocusing just by looking at the sign, because I have enough symmetries here that actually this model is exactly equivalent to if I replace this plus with a minus in front of the nonlinearity. So the sign itself is not helpful at all. I have to work a little bit harder. So I will show you some equivalent models to DNLS. So if I do a change of variables, I can turn DNLS into this equation right here. Now you see I have still the linear Schrodinger equation, I have a cubic derivative nonlinearity, but now I have added a cubic nonlinearity without the derivative and a constant k in front of it. And I can take this k to be positive, negative, as big as I want, right? So you can imagine that, well, if k is very, very large and it has the right sign, then this part right here should be focusing and it should dominate. Right? So maybe I expect that the behavior of DNLS should match the behavior of the focusing cubic nonlinear Schrodinger equation, right? even worse than that, I can use this change of variables and now have, okay, this beautiful equation right here. What do I have here? So again, linear Schrodinger part, two terms where I have, cubic nonlinearity with some derivative somewhere. And then I have here this term with a very, very big potentially coefficient with quintic nonlinearity. Okay, so again, if I take nu to be large enough, I expect this part of the solution, this part of the equation to dominate. And so then what do I have? I have the focusing quintic nonlinear Schrodinger equation. But this equation, actually, we know about its well-posedness. We know that global well-posedness for large initial data fails in L2. So my hopes are already diminished a little bit, right? So what I've shown you so far is perhaps an indication that there is some focusing behavior hidden in DNLS, right? And now to seal the deal, this equation has solitons. If it has solitons, it has to be focusing, okay? I do have a lot of solitons. I will only show you two kinds, the algebraic soliton, which looks like some profile that is going to, as we evolve in time, travel in space and also oscillate in time, okay? So here in blue is the real part of the initial profile, and in orange is the real part of the solution at a later time. Okay, you should also imagine that traveling, but that looks better like that. Okay, and the other important soliton solution of DNLS is the stationary soliton, which has a profile that now doesn't travel, stays stationary, and it just oscillates in time. Again, the blue is the real part of the initial data, and the orange is the real part of the solution at a later time. So it doesn't move, just oscillates. Okay, so I have solitons. It's a focusing equation. I should be quite scared. Now, I want to show you what was known when we started looking at this problem. First of all, local well-posedness in HS for s greater or equal to 1/2 has been known for quite some time. But together with that, we have an ill-posedness result. We know that uniformly continuous dependence on the initial data is going to break down below s equals 1/2. Okay, so I am going to have this, this region where I'm not green anymore, and I don't know what I'm going to be. Now, how do I go from local well-posedness to global well-posedness? The local well-posedness result above gives us a nice indication of what the time of existence is. It tells us that it only depends on the h1/2 norm of the initial data. So now I hope that, okay, if I could get nice a priori bounds for my solution, then I could perhaps iterate this argument, right? Create a lot of local solutions and then glue them all together and get a global solution. And how could I get this a priori bounds? Well, I have all of these conservation laws, infinitely many of them. One of them really looks like the h1/2 norm. I could use them to get a priori bounds. The problem is that this fails here. And the conservation laws are not good enough to give me a priori bounds. And the problem is lack of coercivity, right? Control of the conservation of the conserved quantities does not give me control of the HS norms. So after that, the majority of global well-posedness results, the idea behind them was just to somehow get yourself in the coercive regime. And the way that was achieved was by assuming something additional in the form of bounds on the mass. Okay, so under the assumption that the mass of the initial data is less than 2 pi, they were able to prove global well-posedness first in H1 and then all the way down to H1/2, matching the local well-posedness theory. Of course, the question remained: is 2 pi the best thing that you can do? Is that optimal? This bound. The answer is no. And it took actually a very long time to break this threshold, 20 years. And then the next big group of results where it was able to prove global well-posedness under the assumption that the mass was less than 4 pi in H1 and then in H1/2. Again, is that optimal? Before I tell you if it's optimal or not, I need to tell you that 4 pi actually here has a significance. 4 pi is exactly the mass of the algebraic soliton. And what we found when we started looking at the problem, which hadn't been noticed before, is that 4 pi is the absolute threshold below which, or above which, whatever way you want to look at it, the conservation laws are going to lose their efficacy to control Sobolev norms. And we have a very explicit example for that. So if I take the algebraic soliton and I rescale it, I'm going to get a family of solutions. As it turns out, they all have exactly the same values for their conserved quantities. Their mass is exactly 4 pi for all of them. And all the other conserved quantities are 0 for all of them. So exactly the same conserved quantities for all of them. But this family is unbounded in HS for all S positive. So there's no way, once you have mass greater than 4 pi, to just use the conserved quantities, no matter what clever way you combine them in, to control your HS norms. On the other hand, there was a different way to study this equation using the complete integrability and the inverse scattering transform that I mentioned earlier. An important result that I want to mention is the global well-posedness result under no assumptions on the mass of Jenkins, Liu Perry, and Sulem, who proved global well-posedness in H2. So my initial data has to be in H2, but it also has to have spatial decay. Around the same time that we were also looking at the problem, there was a big breakthrough, the result of Bahuri and Perelman, who were able to prove global well-posedness in H1 half using, assuming nothing about the mass for large data. And as you can already tell by what we have seen before, this does use the completely integrable structure of the equation, because otherwise, just using PDE techniques, you cannot do that. So this paper really uses a very a true combination of PDE techniques and complete integrability. So we now know that at least at high regularity, you can have very large solutions for large data, right? But we still have this gap between 0 and 1/2. And I know that if I can have anything there, any kind of well-posedness, it will have to be the yellow kind, right? Just continuous dependence, not uniformly continuous dependence, which means I cannot use contraction mapping arguments. Okay, so when we started looking at the problem, what we identified as the main enemy is the concentration of the L2 norm in physical space. I'm not afraid of the L2 norm growing. It's a conserved quantity. What I'm afraid is the solution concentrating in one or more locations in space. So having something like that, okay? And what can help me prevent that? It's a continuity. So a bounded set Q, subset of L2 is equicontinuous if small translations in space are going to generate small change in the L2 norm uniformly, okay? And you see that something like that is not equicontinuous, right? If you think of this as just 3 snapshots of something that really tries to concentrate in one location, this is clearly not equicontinuous. No matter how small my translation is, at some point, the entire solution will be outside when I translate it, right? There will be no intersection. So what we would like to show is that DNLS has equicontinuous orbits. If I take a subset of L2 that is bounded and equicontinuous, and then I take all the initial data there, and I flow them under DNLS for all the times, and I consider this set Q star. So this set Q star contains essentially anything that can be reached with initial data in Q at any time t flowing under DNLS. So I want to show that this set Q star will also be equicontinuous. Okay. So in our first go at the problem with Rowan Killip and Monica Visan, we were able to prove global well-posedness in HS for S greater or equal to 1/6, but still assuming that the mass has to be less than 4 pi. So we were able to bridge this gap a little bit down to 1/6, but still with some assumption on the L2 norm. So there we proved an equicontinuity result, again, subject to this mass assumption. We proved a priori bounds using this equicontinuity result. Then we used that to prove global well-posedness using the method of commuting flows that hopefully we'll get a chance to briefly show you later. And importantly, we identified the role that equicontinuity plays in the well-posedness theory here. So what I mean by that is that the only place where I actually need the assumption on the mass is to get a continuity. Everything else doesn't require this assumption. I just need it for a continuity. Okay? And also, I want to mention that this proof exactly the same, exactly the same result and exactly the same proof works uniformly both in the line setting and in the periodic setting in both geometries. Shortly after that, Ben, together with Rowan and Monica, were able to remove this mass assumption on the continuity result, and that immediately yielded global well-posedness in HS for s greater or equal to 1/6 for large data. And then, emboldened by these advances, we decided to see how far can we go? Can we prove the conjecture? And we did. So we proved that DNLS is globally well-posed in L2. So we do have the best thing that we could hope for. The picture is now complete. The method that we used is what we call the second generation method of commuting flows. And it is a sharp result, meaning that the picture is now complete. We get the best that we could possibly get. And now you see that there is a little bit of difference with the results that we had before, because now we actually do have global well-posedness exactly at the critical space. Okay, so now, if I have a few more minutes, I want to just quickly give you some idea of the proof. So there was a question for the Lax operator. Here it is. So this is the Lax operator for DNLS, L kappa, and then L naught kappa is what I get if I place in there Q is equal to 0, right? If I take the 0 potential. Then we can consider the perturbation determinant, which is the determinant of the inverse of L0 times L. That gives us an object. It's well defined. We can also renormalize it to get this quantity A kappa Q. Okay, so these quantities A kappa, defined that way, were already considered in the work of Klaus and Schippa a little bit before our work, and they show that these are preserved under DNLS. So they provide new conservation laws for DNLS because I have one quantity for every kappa, right? So I have, again, infinitely many conserved quantities, but different than the ones I had before. Then what we did is, okay, I take the logarithm of this quantity A that I showed you earlier. I call it alpha of kappa. And the nice thing about those is that they admit this nice asymptotic expansion in terms of powers of kappa. And you see here that there is something interesting about the coefficients that I get in this expansion. What I notice is that I recover all the previously known polynomial conserved quantities of DNLS. So I get M, the mass, the Hamiltonian, and then I will get all the rest of them going on. Now here, if I take the real part of this equation, then the mass is going, the first term with the mass is going to drop out, right? And then if I also multiply my equation by 4 kappa, then I will have that 4 kappa times the real part of alpha is equal to the Hamiltonian plus some lower order terms of order kappa to the -1, right? Okay, so what if I throw away the lower order terms? I'm going to get a new Hamiltonian, h kappa, which is equal to 4 kappa times the real part of alpha, and that will be equal to the Hamiltonian of DNLS plus lower order terms. Okay, so as kappa goes to infinity, I expect these to converge. And if I look at the flows that are induced by this Hamiltonian h kappa, I see that they commute with each other and they commute with DNLS, meaning that if you give me some initial data and I flow them for some time under h kappa and then some other time for DNLS, it's the same if I first evolved it under DNLS and then under h kappa. Okay, the order in which I evolve them does not matter. These equations are now much more regular than DNLS itself, so it's easy to show that these are well-posed in HS for every s greater or equal to 0. And the hard part is to show that they actually do converge to DNLS as kappa goes to infinity. You can see that the Hamiltonians converge, but it's much harder showing that the flows, the evolutions themselves converge. But that's exactly what the method of commuting flow, of the commuting flows does. Because, okay, in order to get well-posedness, I don't need to control just the flow of one initial data, right? But I need to control the difference of the evolutions of different initial data. So if I take two initial data, Q0 and Q0 hat, Q0 tilde, okay, so the green arrow is what happens if I evolve those under H kappa, and the blue arrow is what happens if I evolve them under DNLS, and the yellow is the difference, right? So if you give me this initial data, I already know that since the H kappa flows are well posed, then the green solutions are going to be close to each other, right? So now in order to control the difference of the blue solutions, I just need to show that these yellow arrows are small, right? Not just for Q0, but also for Q0 tilde. So I need some uniform result for that, and that's exactly what we showed. We showed that the flow induced by the difference H minus H kappa converges to the identity, okay, in a very strong sense. So uniformly on bounded intervals of time and nice sets of initial data, right? Bounded and equicontinuous. And this part is exactly where our assumption that S is greater or equal to 1/6 was needed, because if you remember my equation, it has a cubic nonlinearity, right? So in order to make sense of the nonlinearity, I need Q to be in L3. And that's exactly what Q being in H16 gives me, because H16 embeds in L3. Okay. Great. Now, if I want to move towards critical well-posedness, what do I need to improve? We already know that the H kappa flows are globally well-posed in L2. That is not the problem. The only thing that is missing is improving this result, right? The convergence of the difference flows. But I already tried to convince you that it was important that Q was in H16 at least, right? So in order to fix this, somehow I would I would need to get some additional regularity on Q, which how will I get that? And now remember, well, that's a dispersive equation. I have local smoothing. So I expect locally in space, on average in time, I can gain half a derivative. Bad news is I don't have local smoothing. And I can prove that to you. So if I take the stationary soliton, I showed it to you for a reason. So if I take the stationary soliton and I rescale it, I will get a family of solutions that have exactly the same L2 norm, but are unbounded in the local smoothing norm. So there is no way to get a local smoothing result uniform for L2 bounded sets of initial data. Instead, I can get a local smoothing result for equicontinuous sets. But even that is not enough, because if I go back here, remember what I need to, the thing that I need to have more regularity is not the solution under DNLS, but the solution under the difference flow. So what I need is local smoothing for the difference flow. But what am I trying to argue? I'm trying to argue that the difference flow converges to the identity. But local smoothing is a dispersive phenomenon, right? I need high frequencies to travel very fast. How is it going to work? Well, what we have to do is discover some residual dispersion in high frequencies, take advantage of that, and be able to get, use this dispersive effect that is left over to actually prove local smoothing. Okay. And I will end here. Thank you.
Thank you, Meryl, for this nice talk. Are there any questions in the audience? Please, if so, please just raise your hands. Welcome.
Do stationary solitons exist in nature or in the laboratory?
You mean if they have been constructed? I assume so. I assume that they must, yeah, but I mean, okay, yeah. Okay, so yeah, solutions like that, where they look like they don't move in space, they just oscillate in time. Maybe not this specific stationary soliton, but there are other kinds of those that are called breathers that look like they have disappeared, but then they emerge again. And that has connections to rogue waves. In the sea might seem calm, but then suddenly there is a huge wave. Where did that come from? Yeah, so they have been observed.
Online,
Yes, I have a couple of questions. So you gave the lax operator, but only one of them. You didn't give the other one, the P. Could you
Yes, I
write
didn't
that
give the
down?
other one because I didn't need it. And I'm trying to spare you the gruesome details. Yes,
But
so
in order to apply the inverse scattering method, you do need to know what the other one is, because you need to have an integral equation that gives you the inverse scattering. So can you at least write down the integral equation?
I'm afraid I do not remember it from the top of my head. If you want, I can send it over to you later. But I want to maybe, okay, that's a good point to emphasize. If I didn't make that clear enough, I'm not using inverse scattering. So out of all these characteristics of complete integrability that I mentioned earlier, of course, I told you that the conservation laws are not good enough to help me after a certain threshold. Inverse scattering, although it's great, it has one pitfall. I need additional decay in space, and I'm not willing to give that up. Okay, so the only thing that the formulation of complete integrability, if you want, that I use is the existence of the lax pair, and I'm only using the lax operator. Okay, so what I'm doing, the way that I use complete integrability is I have my lax operator here. I can define the perturbation determinant, or at least the renormalization of the perturbation determinant, and that is going to be preserved. And that is, that really captures the structure of complete integrability that I need to continue my proof.
Can I slip in another question? Or I don't want to monopolize, but you also you spoke about a Hamiltonian which just came out of the asymptotic expansion, but you never said what the actual Hamiltonian structure is. What is the Poisson bracket?
Yes. Yeah, it is quite complicated. So I avoided writing it down, but it's yeah, exactly. So once I take, I define these Hamiltonians, I use to induce this the flows induced by the Hamiltonian H kappa. I use exactly the same Poisson bracket as for DNLS, right? So that it is consistent.
So, I mean, if I understand correctly, the kappa is just something that's artificially introduced. It's not part of the original DNLS equation. It's the transformation which took you to the other form with some kind of quintic term. Is that right?
The kappa? No,
Yeah.
no. This kappa is it's a spectral parameter.
It's a spectral parameter. So
Yeah.
that has nothing to do with the transformation to the other forms of the equation?
No. The transformations to the other forms were just to give us an indication of we should be afraid. There might be some focusing behavior hiding behind there. Yeah, so it has nothing to do with that, right? It's let me go back. It's the kappa there from the that I also
it's in the
included.
lax operator.
Exactly.
Okay, so but does the Hamiltonian structure depend on kappa somehow? I mean, normally it wouldn't.
You mean the
Well,
what
when
do you
you
mean?
write down the Hamiltonian structure in terms of Q, there's no kappa there. This is just a part of the definition of the lax matrix, right? And the fact that the
Yes.
lax
So okay,
equation
maybe
has
if it helps you, okay, to draw some parallels, the lax operator here really looks very similar to the lax operator for the cubic NLS, right?
Yes.
Yes, exactly. So whatever kappa means to you for the cubic NLS, it means exactly the same thing here.
Well, for the cubic NLS, there's a well-known Hamiltonian structure. In fact, the whole pencil of Hamiltonian structures. And I mean, the kappa is not one of the variables. The kappa is an auxiliary variable, as you say, the spectral parameter, which comes in. It's what gives you an infinity of.
Exactly. Yes. So it's exactly the same thing here. It's just the only problem is that I cannot really extract it from here at all because it is. Well, it's because it's everywhere, right?
Okay.
Yeah.
I think I asked enough for now. Thank you.
You call one of your solitons algebraic. Why is it called algebraic?
Excellent question. Yeah, I don't know. It's I think it has it's yeah, I don't know. The terminology was introduced way ahead of my time, but but perhaps you might be interested to know that there are definitely lots of connections between integrable PDEs and algebraic geometry, which I will not get into too much detail. Perhaps it comes up there. Yeah, I don't know.
Other
You also
questions in the
mentioned
audience?
periodic boundary conditions, but for periodic boundary conditions, of course, you don't have solitons, but you do have what's usually called finite gap solutions. Does that happen with the derivative nonlinear Schrodinger equation? Is there some sort of multi-periodic finite gap solutions that replace the solitons?
Yeah, I'm not sure. But I can tell you, okay, if you're interested in the periodic problem, I can tell you perhaps what the state of the art is. So for the periodic problem, this result right here is the state of the art. So right now, we really don't know if it is possible to have global well-posedness for a regularity below H16, we don't know, or for large data. It is completely an open problem. So also for the periodic problem, even for more regular initial data, we don't know if we can have large data well-posedness. It is, for now, no matter how smooth your data is, we don't know above 4 pi.
So if there are no more questions, please join me in thanking Maria again.